Hello everyone! In this video we will continue to examine topic 1.2 uncertainties and errors, and in particular we will distinguish between uncertainty and error. Alright, in the last video we spent a lot of time, or last few videos, we spent a lot of time distinguishing between random and systematic error as introduced into a measurement. We learned the use of the terms precise and accurate. Now, this is an important distinction. There is a difference between error and uncertainty, between those two concepts. We've already seen error. Error is the deviation from the real or the true quantity. It's in one direction for a given measurement, but for multiple measurements can be described as either random or systematic, and it's relative to the actual value. Okay, the real value that is being measured. Error is the answer to the question for either a single measurement or multiple measurements. How far off were you? Okay, how far off were you? Uncertainty is a related concept. It's a range to which a measurement is known. It's about our certainty of that measurement. High uncertainty means that we're unsure about the measurement. Low uncertainty means that we know sort of a great deal about the measurement. We're very confident about it. And it's quoted as a range. So, for example, if I'm giving a length, I might say 1 meter plus or minus 0.3 centimeters. What I'm giving after this is the uncertainty, not the error. This, despite my own speaking and sort of other ways about which people might speak, this is fundamentally an uncertainty. It's quoted in multiple directions, and it's the answer to the question, how sure are you? Now, why is this so confusing? Why is this often referred to as the error? Why am I probably likely to do that very thing just in discussing it? It's because this thing right here is almost inevitably a quantitative measurement of the random error. So uncertainty is about how sure you are. But almost 9 times out of 10, we don't know the true value when we're actually taking a measurement, particularly when we actually take it before we process it or do anything with it. So what we do is we give an uncertainty that represents sort of our knowledge about how far we could have been off theoretically. And how do we do that? Well, the best way to do that is to take a whole bunch of measurements and use those whole bunch of measurements to figure out sort of the spread in that data, and then use that, known as the random error, on a set of measurements to give the uncertainty. So we represent the uncertainty using the quantitative measurement of the random error. All right? This is going to be tricky, so I'm going to say this a couple of times, and we'll see it sort of over and over, but we are using the random error to give an uncertainty, but an uncertainty is about us. That means you don't need the random error to give an uncertainty. If you take a single measurement, you cannot possibly have measured the random error, but you can always give an uncertainty. If you measure a time and it's 1.2 seconds, but you're a little bit unsure about it, you think maybe it could have been a little more, a little less, you might represent that time as 1.2 plus or minus 0.2 seconds. And in that case, you're simply estimating the uncertainty. Anytime in this class you take a physical measurement, you should estimate the uncertainty, okay, as best you can. There are a couple different ways of doing that, but the truth of the matter is it should be a genuine estimate of the range to which you know the measurement. You could get it wrong. That happens. But it should be a best estimate of how sure you are of the value that you just measured. Here's another example. If I'm measuring sort of the time it takes for that ball to drop from the table to the floor, and I measure that time as 0.9376 seconds on my stopwatch. Okay, that's what the stopwatch says. Is that So I now look at that and I say, oh, okay, therefore I know the measurement to plus or minus 0.00001 seconds. Now, that is totally unreasonable. Okay, there's no way. Why? Because quite obviously, other methodological uncertainties introduced by, or methodological errors introduced by sort of the actual timing process, like hitting the stopwatch button in that example, are going to mean that you simply don't know the value to as many digits as you just gave. So if you tell me that your uncertainty is plus or minus 0.00001 seconds, simply reading it off the instrument, I'm going to turn back around and say, that's not a very good estimate. So you want to be at least in the right ballpark. Complicating the difference between error and uncertainty, unfortunately, is that uncertainty is represented on graphs using what are known as error bars, and I'm so sorry about this. So we use the random error to get the uncertainty, but even if we didn't have a measurement of the random error, you can always and should always represent the uncertainty on your graph. And the way you do it is by using what are called error bars. I'm sorry about that. That's just sort of how it goes. If I could rewire everyone's brains, I'd say call them uncertainty bars, but you have to be a little bit careful. In novel scientific research, true error is almost never known because the true value itself isn't known. Therefore, the error given is almost always a measurement of the random error and is representing the uncertainty on the measurement. And the uncertainty is almost always the uncertainty solely due to that random error. In this set of videos, you should make sure to work on the example problems and work through the solutions as shown in the slides.